Okay, so what I thought I'd do would be to derive the at least the start of generalized principal component analysis, and I'm going to operate out of chapter 3 of the notes. Everybody has chapter 3, I presume, right? So let's see. What is the outer limit of where I can go? Is this Khosrow, how far can I go here? I guess he can't really tell me. How about if I do this? Okay. Chapter 3 of this book, and it's called Algebraic Methods for subspace segmentation, multiple subspace segmentation. Okay, and the general plan in this chapter is to try to give at least an algebraic solution to the problem of segmenting points. So let's just a few definitions and then we'll get started. So you know the problem actually has connections with Hilbert's 16th problem, and so there's some terminology that we borrow from that part of mathematics is called algebraic geometry. So you call a definition a subspace arrangement script A. The formal definition is in the note, so I won't write it all out. Is a collection of subspaces in R sub D. The SI's subset of R sub D are subspaces, and the dimensions of the SI's, the dimension of SI equals n sub I. Oh, sorry, d sub I, little d sub I, and you know, Z sub A is the union of these subspaces, S1, S2, Sn. So just to tell you about the subspace, just to tell you why this is called a subspace arrangement. So I'll draw a picture in R3. You know, an example is here's subspace S1 and here's a subspace S2. All subspaces have to go through the origin. Right? That's the definition of a subspace. And a subspace arrangement is the union of subspaces. Everybody remembers that the union of subspaces is not a subspace. Right? So it's not a subspace. It's, however, an example of what is called an algebraic set. And let me just sort of let you explore this in talk a little bit about this. So the notion is that in algebraic geometry, the way you represent S1 is you say that there's a polynomial or a set of polynomials, I'll just call it PS sub 1, a set of polynomials P11 up to P1m of x that vanish on the subspace. So it is called the zero, it is the zero set. Algebraic sets are zero sets of algebraic functions. That's what an algebraic set is. So it is the point, S1 is the set of all x's, P11 equals P12 equals P1mx equals 0. And you know, if there are subspaces, you have a sense that the number of equations m is you know, is capital D minus D sub j. It's the complementary dimension of the dimension of the subspace. There are as many, so if you know, the capital D dimensional space, so there are this many constraints, what's left is D sub j. So if this was Sj, that would be Pj1 and Pj, Mj, and this would be Mj equals capital D minus D sub j. So that's what the thing on the indices is. Of course, you can see, you know, this methodology is good enough to also cover curved surfaces or manifolds, because, you know, if S1 actually had been a curved surface that was represented by this, so long as these were polynomials, you know, you could get a curved surface. You can really see it's easy to, you can see cylinder, you can get circles, you get cylinders, you can get cubics, quartics, you know, 0 sets of surfaces. And so that's why algebraic sets are rich. You know, subspaces are a very specific case of algebraic sets. Okay. Now, what's the problem with algebraic geometry? So you can say it's the 0 set of polynomials. Now, the problem is, once you have this set of polynomials equal to 0, can you say that this is somehow a minimal description of this, how you describe this algebraic set? And the answer, the technical difficulty here is that if you multiplied each one of the polynomials by some factors, qj1, qj, m sub j, etc., you know, once you define it to be the set of all x's, but this polynomial vanishes, you know, you multiply that by any other polynomial, that the product of those two polynomials will also vanish. And the way people deal with it if x was a single variable, then in some ways you say if this is prime, then it doesn't have any factors, and this is, you know, it's easy to figure out what a minimal description of it is. However, with multivariate things, x1, x2, etc., it's not as easy to figure out what primes are. But there is a machinery in algebra for thinking about these things. So you call these, you say that x is, if you say x is the set of all x's where some polynomials, and now I'll use this qji of x equals 0, I equals 1 to m sub j. If you say, well, you know, is it possible to define this, then there is a choice of these qji's for which this thing is so-called prime ideal. So these things are called ideals because the space of polynomials where something vanishes has got an algebraic identity. It's called an ideal when you multiply the polynomial by something, you still stay in the same set, and that's called an ideal. So, you know, I don't want to get too bogged down. There's an appendix called Appendix Appendix C, which talks about ideals. I will get back to it. But, you know, the problem with really just trying to do this with algebraic geometry is you get bogged down in this computation of prime ideals. And if you're not careful, you know, it's hard to, you won't get a minimal representation of these polynomials. You might get some junk multiplying them. And then it's a question of being able to factor them out. Okay, so, you know, part of what Hilbert's story was how do you factor out these prime ideals and so on and so forth. Now, in some ways, the set itself is, you know, the set itself is, there's no ambiguity about the set. There are many different ways of describing it, but so long as the ideal that describes it is a prime ideal, or it can be broken up as a union of prime ideals, this is okay. So that is part of the challenge about just relating it directly to algebraic geometry. So I want to now back off from that algebraic geometry and return to our subspaces. And here, you know, what we have going for us at the outset with subspaces is that all these polynomials are linear polynomials. You know, they're just the way you parameterize subspace is you take all the normal vectors to that subspace. If the normal vector is bj1 transpose x, bj2 transpose x equals ... equals bjmj transpose x equals 0, where the bji's belong to R sub d, x is in the ambient space, And these are the normal vectors associated with the subspace. The number of normals has the complementary dimension. That's how you parameterize it. Then how do you describe a union? Well, you have one of these sets of polynomials for each one of the SI's. And the union means that you take all the products. So for instance, if you had S1 is x of P11 x equals P1 m sub 1 of x equals 0. S2 was x P21 of x equals P2 m2 of x equals 0, where all of these are linear polynomials. The way you describe S1 union S2, so union is an OR, belongs to either S1 or S2, and then you just take the set of all possible products of these. You know, it's a set of P11, P21, P11, P22, P11, P2, M2, P12, P21, P12, P22, etc., up to P12, P2, M2, and you keep going to P1, M1 times P21, P1, no, P2, M1 times P22 up to P2, no, P1, M1 times P2, M2. All of those equals 0. Now it's all the possible pairwise products. So the number of equations that you get is M1 times is M1 times M2 equations. It's a lot of equations, except, you know, in the case where Mj is equal to 1. You know, what is Mj equal to 1? It means a single normal. Single normal means it's a subspace of dimension d minus 1, you know, 1 less. So if it was that we were trying to segment the space where everything was of codimension 1, m sub j is called, dj is the dimension, m sub j is called the codimension. So if everybody is a codimension 1, which is two-dimensional subspaces in R3, then, you know, m1 is 1, m2 is 1. It doesn't matter how many of these there are. If it's S1 union S2 up to Sn, it doesn't really matter how many there are. There's just one equation. You know, it's P1 is P11 times P21 times Pn1 equals polynomial of x equals 0. And each of the Pi's are linear functions. So the product of them is an nth order polynomial. So the order of this polynomial is the number of subspaces. What about here? You know, even though each one of those were products, if each one of them were linear, then all of these are quadratic polynomials. So the order of the polynomial here is equal to the number of subspaces. But the number of polynomials is the product of these codimensions. It's this product I equals 1 to n m sub I should say j equals 1 to n m sub j is the number of equations, but the order of each of those polynomials is equal to n, which is the number of subspaces. Right. So in abstract terms, so why am I telling this to you? I'm deliberately, you know, by the way, this is, if you're feeling it as heavy going, even though it's all counting, we're going fast. It's, even though this is elementary sounding, it's not so elementary, let me say. So, so you know, the abstract problem here is that if you are given these sets, then you're asked to find these polynomials, and then you're asked to factor them. For instance, if somebody told you that you had n subspaces of, and what would this correspond to? So this corresponds to n subspaces, each of dimension d minus 1. one less than the dimension of the ambient space. So what you are asked to do is find for me that nth order polynomial that vanishes on that subspace arrangement, and then factor it into those n linear factors. That's what generalized principal component analysis is, because once you've factored it into those n linear components, each one of those linear factors gives you the equation for the normal. And you're done, because once you have the normal. So why are we making such a big deal out of this? Well, this is not, and this is how Hilbert posed his problem, but Hilbert, like a good mathematician, obfuscated it and said, find me the ideal. If you are given a vanishing ideal on this set, then break up that vanishing ideal into n prime ideals whose intersection that ideal is, which means, so that's the algebraically correct way of saying this while taking into account all these factors and all of that kind of stuff. We will do it. It's not difficult, but let's not make our lives complicated now. But that was the problem that he posed. Now, what makes life hard for us is that we're not given this entire subspace. You're just given a bunch of points. Right? And so you're just given points. You're not told how many of these subspaces there are. And you get to figure out, which one of these points deserve to be flattened out to be S1, and which of those other points deserve to be flattened out to be S2. Sometimes it can be quite ambiguous. It could be that someone in R3 gave you data. It's like this and then like this. So, when somebody gave you data like this, you could say, well, a really good fit for it is a two-dimensional subspace that lives here. Or you could say, well, actually there's further structure inside the subspace, because here's S1 and here's S2. And so, the problem is a little ill-posed in terms of what, when somebody just gives you points, the question of how far down the food chain you go is good. And, when the points have noise, they don't exactly lie on the subspace. It also gets to be quite interesting. So we'll spend a lot of the course sort of fixing noise outliers. Whenever someone, from this time, I guess in high school, when somebody asked you to fit y equals mx plus c or something like that, that even if you got one bad data point, even if you've done all your experiment perfectly, but your lab partner screwed up and you got one data point like this, if you then sort of run this y equals mx plus c, you get a fit which looks like this, because this point sort of pulls it down, right? So outlier, all of this linear regression, which is what we are doing, we're calling it principal components analysis, which is the souped-up version of linear regression, are very, very sensitive to outliers. In fact, how did you deal with this how did you deal with points like this? You must have had to deal with this in or college or something, whenever you are confronted with a laboratory notebook, just be bold and guess as to what you do. Ignore that point. Exactly. That's exactly the correct answer. Right? You're better off dismissing this as an outlier, throwing it out, and then doing the fit. The problem is that one person's outlier is another person's noise. Right? And so the question is, when do you decide something is an outlier and when do you think something is noise? And we are absolutely going to hit this head on. This is actually Alan's baby. Alan's really, this is what keeps him happy, make distinctions between outliers and noise. So we'll have a great deal to say about this. But before we jump in, I'm going to give you sort of the noise-free story. The noise-free story actually is surprisingly simple. So let's dive in and let's try to start solving this problem for the subspace case. In fact, once we've done the work on the subspaces, you can soup it up to some extent to deal with quadratic, cubic, and other surfaces. Even though one of the reasons that Dheeraj is now sitting in on the class he's going to be very critical of changing these methods to nonlinear polynomials, because there are some real problems which we'll point out to you and which Dheeraj is going to see if they're worth fixing. Okay, so the first thing before we do this is a without loss of generality thing, which I want to do a little bit of gardening to get started on this. So first question that arises is, why do we have to insist on the subspaces going through the origin? Do the subspaces need to go through? How about if Si was the set of all x's where you had, well, what if it, okay, let me just draw a picture. What if what you were trying to do was trying to segment data, which actually I don't want things to cross. I guess green is probably not a good color for the camera to pick up. Actually, I fear for the folks at Merced that I'm obscuring the blackboard, but maybe they'll complain to you. Is that possible? If someone gave you data like this and the axes were like this, so this was x1 axis and this is the x2 axis. Now these are not subspaces. They don't go through the origin. However, they're not off by much. You know, they're affine translates of subspaces. So how do you deal with affine translates of subspaces? And the answer to that is that there is sort of a standard hack for dealing with. So these things are called affine. You know, the correct term is the affine translate of a subspace of a. I put that in brackets because some people just call it affine subspaces. You know, the word subspace, you know, if you're really doctrinaire, has to go through the origin. So the word affine subspace is a contradiction, but you know, we can allow for it. So what do you do with things like this? You know, here, so the prescription is, now I'll just do it in RD. So what you do is that instead of having subspaces, if the SIs were this, then what you do is you take the coordinates of a point and you add 1 to it. So you take a point in RD and you add an extra dimension 1 to it. These are called homogeneous coordinates. You know, our friends in graphics are responsible for this terminology. And the reasons we're doing this is, you know, if you had the points like this, they lie on a space of the form x2 equals mx1 plus c. Right? That's what one of these lines look like. So instead of writing it as a subspace, you could write it as m1, 1. Oh, sorry. What do I want to say? I want to say, yeah, I guess that's okay. m1 c minus c, x1, x2, 1 equals 0. So, you know, this affine coordinate is the thing that multiplies the 1, and it still looks now like a, you know, so it now looks like a subspace in this higher dimensional space. And the way that one makes sense of this graphically is to say that what you're trying to do, in effect, is to embed these affine subspaces in a space of 1 dimension higher. So if I had drawn the same picture, and this was the x1, x2 space, and these 2 points were like this as I've drawn, in effect, what I've done is I've added an x3 coordinate and put this at x3 equals 1. So maybe I should draw the x3 below here. So here is still x1, which is parallel to that, x2. And this is the x3 axis. And this plane is the line at x3 equals 1. Right? And then these things, if you wish, what I've done is I've taken a subspace which goes through the origin. So what this describes is a subspace going through the origin, which includes that line, going through the origin of this d plus 1 dimensional space, which goes through the line. And the same for this. So by this little hack of adding 1 onto this, you take the affine translate of a subspace and you make it, it becomes homogeneous. And that's why these are called homogeneous coordinates. They take affine equations and they make it homogeneous. Does everybody know the graphics story? You know, in graphics you have points in R3 which you want to rotate and translate and so on and so forth. And it's, when you want to do a rotation plus translation of this, a rotation of this looks like R times x plus p, where p is the t for translation, r for rotation. So that's a affine transformation. If you want to take this point x, rotate it, x belongs to R3, and then t belongs, R is a rotational matrix, 3 by 3. Does everybody know what this term means, SO3? SO3 is a 3 by 3 matrix, special orthogonal matrix, which satisfies R transpose R equals I. It's a rotation, and determinant of R is +1. And the determinant could be -1, and that's the S, the specialty of this thing is that its determinant is +1. So rather than write it as a translation plus rotation here, the graphics guys, and in all their graphics processors, they want to make that linear algebra, so they do this. Right? Because this is a way of doing Rx plus P as a single matrix multiplication by bordering the x by 1, putting 3 zeros below and then 1. Sometimes they use this number also, and they use this alpha for scaling, for scaling the size of the, but, that's where this term homogeneous coordinates comes from. It comes from bordering the x's by 1s. It always has the effect of taking affine translates of subspaces, embedding them in a higher dimensional space. And so, if these were affine subspaces of di, if these were affine, if this was, let's say, if I had an affine subspace here embedded in, if these were affine subspaces in Rd, then in homogeneous coordinates, they'd become di plus 1 dimensional spaces embedded in Rd plus 1. So the extra dimension gets added on, and the dimension goes up, right? Because these were both one-dimensional subspaces. When I embedded them in R3, they became both two-dimensional subspaces, because this extra dimension, this homogeneous coordinates, gives you that extra dimension. So that's one little hack. And last time I don't remember if I was telling you. By the way, I was telling you about the Swedish truck company guy who'd been in my class and who tried to apply this, and I couldn't remember the truck company, and you said it was Volvo. It wasn't Volvo, it was the other truck company, which I remembered after class, and I guess I've now duly forgotten again. Okay, it'll come to me before the end of this class. No, Saab doesn't make trucks. It only makes jet planes and fast cars. So, what's it called? Scania. Okay, it's not such a well-known truck company. It's called Scania. Actually, it is owned by Saab, but they don't sell it under the Saab brand name. They're thinking it might dilute their brand name, I guess, to have Saab trucks. But Scania is the name. So this guy, he wanted to, he had GPS data of trucks, X, Y position, but then he wanted to be able to build elevation maps of the highway from this, and he said the good fit for the highway is a piecewise linear fit to it, and thus was the subspaces. Of course, they don't go through the origin because, he had truck data like this and then like this and so on. So what he really wanted to do was fit these hills to it. Of course, the problem for him is this dimension is very long compared with that dimension, because altitude changes are not kilometers, but hundreds of meters at best over several kilometers. And then, he was measuring this in, if x1 was the distance, he was measuring this in kilometers, he was measuring this in meters, and he's stuck on the 1. And, you applied it to the data, all hell breaks loose because, the conditioning is not so good, right? And you can, depending on the units, you have to choose the units so that these x1s, x2s, and 1s are all sort of the same size. Otherwise, the numerical conditioning gets shot to hell. And I must confess, there's no conceptual way of talking about how you do that. You have to massage the data beforehand to make sure that these quantities, you can always do it by subsuming that inside the M and the C, but you do have to do this as a prior step before you start. Okay, so that's the story about affine subspaces. Now, the easiest case to treat, of course, is the case where the subspaces are all of dimension 1 less than the ambient space. But before we do that, let me revisit that scattering of 1D points. I had these examples of segmenting data into several points. Oh, do I want to talk about projections? Okay, let's just do segmenting points on a line first. So this is x is a single variable, and you're given a bunch of points here, a bunch of points here, and you're asked to find the clusters and the cluster centers. So why would you care about this? Well, some problems in vision that immediately come to mind is you have an image I, which belongs to R n by n. And let us say that you record the intensity values of each of these pixels. So I sub ij is the intensity of the pixel at the ijth location, at this location, I and j. And you might ask yourself, can I take a look at the data that comes out of just this intensity map? You just plot the intensities. A point here is here because this is actually the intensity value. It's a scalar value, just the magnitude of this. It's a grayscale image. So you just plot the magnitude of it. You might ask yourself, can I break this up into white, high intensity, black, low intensity, and gray 1 and gray 2. In which case, it is a way to segment the data, segment the picture into some areas which are white, other areas which are gray 1, other areas which are, so this could be white, this could be black, and here could be gray 1, and the rest could be gray 2, for instance. Now that'd be interesting because, as I had shown you these pictures of all these penguins and dancers and the baseball catchers and so on and so forth. It's actually possible to segment the image into a background which was sometimes colored white. And catchers, this catcher had a gray, gray sweatshirt and white pants, and it was it's all a way to segment the image into different pieces. So this image segmentation is one place where this comes up, and that's already, this image segmentation is sort of is a substantive business that in the computer vision community, it's one of the abiding joys of computer vision is to segment images and compare how the segmentation compares with our own gestalt of what the edges of the image are, and so on and so forth. So that's a reason that one might be interested in segmenting data on the line. So the question you ask yourself is that you're given a number of points, xi, I equals, you're given n points. No, what is the notation? Capital N points, is it? Capital N points on the line. and you are asked to figure out how many groupings there are of these endpoints. And figure out the centers of these. Let's call them mu1, mu2, etc. So figure out, and these are the centers of the clusters, mu(i), cluster centers. Figure out how many cluster centers there are. Mu(j), say j equals 1 to little n. Everything belongs to R. The xi's belong to R. The mu(j's) belong to R. Right? And so how do you solve this problem? So I'm going to try to do this a little pedantically, even though it might be quite obvious as to how you do it. Well, you know, if it sat right on top of the jth cluster, does everybody understand this? So you're going to stop me if there's some question. So if a point x belonged to the jth cluster, it would satisfy x minus mu(j) equals 0. You don't know how many, so n is unknown, so you get to figure out n. You know, n can be as big as capital N. If it turned out that the data was all evenly distributed and there was no way to cluster it, you know, maybe n would have to be capital N, and every point has its own cluster and nothing else. But presumably you would be interested in cases where little n is really small. The number of clusters is small, because then it enables you to, like here, you know, you can sort of see that the data is in 4 pieces. Okay, but how do you try to figure this out? So depending on the number of clusters, you know that x, so if you know that x belongs to this, or the logical or, so the data set x consists of the set of all x's, where x minus mu1 equals 0, or x minus mu2. So everybody know this logical or x minus mu n equals 0. The logical or in algebra terms just becomes a product. X minus mu1, x minus mu2, x minus mu n equals 0. This is the product. If it has to be 0 or this has to be 0, it's as good as saying the product is equal to 0, and that's an if and only if. There's no change in notation, and the notation we have in the book. So what's the order of this polynomial? This is a polynomial of order n, and it is a polynomial of nth order, which we can write as sigma k equals 0 to n ck x to the power n minus k. That's what we call it in the book. So Pnx equals 0. So you don't know these coefficients, you don't know the order. What you do know is that you're given these capital N points. You're given all of this. That is given. You're given this, and you've got to figure out the polynomial and the order of the polynomial. So how do you do this? And you want to do it as far as possible using linear algebra. So what you do is you just stack it up and say, if there was a polynomial, if it was true that there exists a polynomial Pn of x that the data lies on, it should be true that Pn of x1 equals 0, Pn of x2 equals 0, and so on up to Pn of x capital N equals 0. And there's a bunch of linear equations. They all look horribly nonlinear in the x, but that shouldn't bother us because the x's are given numbers. It's the CI's that are unknown. Yeah? Yeah. Is the yeah. So I'm trying to describe the set of data as the x either belongs to cluster 1 or cluster 2 or cluster n. And the value of x is in the set 1 to 4 or whatever. Yeah, so capital X are the intensity value. So what I've done is I've listed all, if you go back to the example, I've taken I11, I12, etc. up to INN, these n squared points, and I've stuck them next to each other, and I call that x1, x2, and I shall call yeah. No, this is rank chaos, so let's just call it. Look, there's no uppercase here, x1, x2, x. But this is a variable, and that's a fixed. This is a data point, and capital X is the set. Is the whole set. It's just this. Is the set of all x's.
So in order to fit this problem into GPC, you also have to think about that as an affine situation, whereby those clusters they don't pass the origin.
So here these are not subspaces, but we'll convert those to subspaces. But that's not his question. So I think his question is about notation. Notation. So capital X is the space, is the set of all the intensity values. I'd like to describe it algebraically as the set of all x's where x minus mu1 equals 0, or x minus mu2 equals 0, or x minus mu1 equals 0. And so little x is a variable here. So I guess I should say little x is a subset. Yeah, it's a subset. In this case, it's in one dimension, it's exactly the same. Confuse it to write it as subset. Let me just say equals. See, if all the data was either in mu1 or in mu2 or in mu(n), then I could have written out an abstract description like this. Of course, you'd just solve it. This would say x is either mu1 or mu2 or mu(n). And that's the solution of this set of equations. But you don't know what mu1, mu2, mu(n) are, and you don't know how many clusters there are. So the notation capital X is the data. This is the data. This is the algebraic description of the data, and I'm writing it out in symbolic form with little x as the variable, as the algebraic variable.
Are we saying that the individual clusters? Sorry, you did this the other day, but they're not like clustered around mu1. They all are
exactly at mu1 because I don't have noise. Yeah, if they were clustered around mu1, that would be 0. And we'll first start with a noise-free case, and then we'll deal with. In fact, I will do it right now. So, good. So the way to write this out, to write these equations out, is as far as the first variable is concerned, the first equation is concerned, you write out little x1 to the power n, x1 to the power n minus 1 up to x1, 1, and times 1 c1 up to cn equals 0. And the reason you have a 1 here is because the coefficient of x to the power n is 1. But you write out the same thing for x2 as well, x2 to the power n, x2 to the power n minus 1, x2, 1. And you keep going till you have n points, capital N points. So you have capital Xn to the power n, capital Xn to the power n minus 1, capital Xn 1. So now this matrix, this is a data matrix. It's actually a matrix of all powers of the data up to up to power little n. Its dimension is little n by n plus 1. And the reason it's n plus 1 is because it's x, x to the power 0 is the other power that's included. Okay, so this is this matrix is given. Well, it's sort of given because you're not given n. But now we'll figure out. So let's call this matrix V sub little n. So V sub little n is a capital N by small n. Presumably you're trying to make n to be much less than capital N, and certainly little n is never going to exceed capital N. You know that at little n equals capital N, there's always a solution because that corresponds to each point belonging to its own cluster. So what is this thing trying to do? This thing is trying to say that this vector, let's call this vector C, which belongs to n plus 1. C belongs to Rn plus 1, is in the null space So C belongs to Rn plus 1 belongs to the null space of Vn. Okay, but you don't know what n is. So what you try to do is, I'm going to try to sneak up on what happens, how you figure out what Vn, what n is. So what you do is you start building these matrices. You start with V1. So V1 looks like x1, 1 up to capital Xn1. So that's a n by 2-dimensional matrix. You take a look at the null space of this matrix. Take a look at does null space of V1, so does there exist a question mark, there exist, does there exist, does there exist a null space to V1? So what do you mean there exists a null space to V1? You know, this it's a long skinny matrix. You know, capital N is large and there's 2 columns. But what if it has a null space? If it has a null space, that corresponds to the fact that everything is in one cluster, right? Because the null space has some entry. This may not be 1, by the way, and this may be, so its null space may have some entries, XX, XX out here. Now, the first entry had better be non-zero because, you know, the second column is all 1s. And so if that entry was equal to 0, there won't be an answer. So you could rescale the first, because the null space, if something is the null space, any multiple of it is the null space, so you can scale that entry to be 1. Andrew? That was the question, yeah. So that's the reason why you can always put a 1 up here, and that would give you the single center, mu. But if there is no null space, you know, it could be that the rank of, if the answer is no, and that is rank of V1 equals 2, then you decide you do V2. V2 is x1 squared, x1, 1, x2 squared, x2, 1, and so on up to xn squared, xn 1. And that's V2. And then the same question, does there exist a null space to V2? Or actually, rather than there exist a null space, let me say, is rank V2 less than 3? Why, if the 3 columns were independent, then there's no null space. And so then if the rank of V2 equals 3, if the rank of V2 is, if the answer is yes, then number of clusters equals 2. Because there's a quadratic polynomial, and the quadratic polynomial means that P2 is n equals 2, therefore there's 2 clusters. So as an algorithm, and there's a little proof there that goes along with it, but at this point, if I just stated it, it would not be a big surprise to you. It says the first j, the minimum value of j, at which n, so the number of clusters, the formula for number of clusters, n, equals the minimum value of j, min over j, the value of j at which the rank of Vj becomes equal to j. Recall that Vj is a matrix that belongs to n cross j plus 1. So it drops by 1. It can't be any bigger than j plus 1. See, the rank of this, so because capital N is, capital N exceeds the number of clusters, or it's equal to the number of clusters. So the rank of this is at least, you know, is not the number of rows, it's the number of columns. And so the place at which it drops by 1, that's the order of the polynomial that vanishes. And you get the, and as the null space, if you normalize the null space to have a 1 out here, then that gives you the coefficients of the vanishing polynomial. Once you have the coefficients of the vanishing polynomial, then you write it out, and it's x to the power n plus c1 times x to the power n minus 1 plus cn equals 0. And if you had this routine which divided it, x minus mu1, x minus mu2, x minus mu n, then, provided these roots were real, then those would give you the cluster centers. And how do you find the roots of a polynomial? It's that you just turn it over to MATLAB. But what MATLAB does is it converts it to an eigenvalue problem. Right? There is this routine. It's just called roots, right? I think that's what the MATLAB. Anybody remember what it's called in MATLAB? It's called roots, I think. Or if worse, don't build that super diagonal ones. That's not, it's a numerically bad thing to do. If you leave MATLAB to its own devices, it'll do a more intelligent thing than simply build that super diagonal, the companion matrix with this in the bottom. Okay, so so this is the noise-free case. So how do you deal with noise? Let's do it without any sense of theory. We are going to do it with a sense of theory, but if you're just going to hack, what you do is wherever you see rank, you'd start thinking about a numerical way of getting the rank. You say, generically the rank of Vj would be just j plus 1. So what you should do is actually take a look at the singular values of Vj. And if there is a certain point at which one of the singular values drops below a certain threshold, so you say the singular value of Vj is less than epsilon, you really say the rank is at least or exactly one of the singular values less than epsilon, where you set epsilon to be some threshold based on the noise. Then you call that you say that's good enough. And then how do you get the null space? It does it's generically full rank. What you do will be you'll get the singular vector corresponding to that smallest singular value and call that the C's. And then you'll feed it into MATLAB, and all of these will be complex. So if you were to hack through it, you just throw away the imaginary parts in the hope that they're small, and they are. And that's a way that it's used. And in fact, in all those initial simulations that I showed you, that's exactly what was done. We set a threshold epsilon based on our estimate of the RMS noise that was there. And we took those images, and amazingly, those images, they're quite, those were real images, they were, you could segment them into 3 groups, it was not even gray 1 and gray 2. It was pretty good to segment them into 3 groups, white, black, and gray. And and then you just go back to the image, and you reveal what was white and what was black and what was gray. And amazingly, it actually makes sense from a Gestalt standpoint. And that's truly surprising because, when you took all those intensity values and you stack them up as a bunch of numbers, any of the semantics of the image was lost. Right? You didn't actually care about where the pixels came from, that they were adjacent pixels, all of that just got washed out. And, and still it was good enough to be able to. And I have to say that Renee, hi Domenico. So Renee actually first got excited because the seemingly, really sort of low-grade hack without, without paying attention to where the image came from, and there had been people who had been doing contour tracing and all kinds of fancy ways of drawing edges around images and edge detectors. And here was a way of just segmenting the image based on sort of turning this crank. And the turning the crank consisted of taking, quite large numbers of points and cranking out the singular values associated with them. Okay, so the question is, can you do more than this? And the answer is you can. And I'm going to do the case of, rather than now, in the book, we then start talking about, okay, so Alan made a point about how you should think about this. Since x minus mu1 equals 0 is, in R1, this is really the affine translate, the only subspaces that are dimension 0 in R1, and so this is like an affine translate of a subspace. So he says that, really what you're trying to do is adding on this point at 1, and you're actually finding subspaces that go through all of these clusters in R2. And there's a story in the book, which I think is worth reading. Let me dive into this segmenting hyperplane story, and we can actually do this today. Are you very comfortable with this? Because this is really quite simple looking, but this is really the heart of the matter. Now it's all just going to be fancier notation to do a lot more. Oh, yeah. 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 Yeah, those are all real images with noise.
Right. So you're saying...
and we did this sort of hack. Instead of the rank of Ej, we kept computing the singular values. And the first value of j, at which a singular value of Vj dropped below this noise threshold epsilon, we said that's the number of clusters.
And so that threshold, like if you set that threshold arbitrarily low, you'll just get like...
You'll get more clusters.
You get like 255 clusters.
That's right, yeah. If you make the epsilon too small, then you'll get tons of clusters. If you set the epsilon too high, you'll get fewer clusters. And I think Rene was determined to get 3 clusters, and so he set his epsilon. But as it turned out, it's actually quite robust, to the choice of thresholds. So, good. There is a nice problem in chapter 3. Okay, so since you asked for it, let me... one of the things that inspired Rene was that there was a thing called, it's actually exercise 3.3, 3.3, I think. There was a technique that was making its rounds called, which is still quite popular, it's called spectral clustering. It's exercise 3.2. So let me just do exercise 3.2. I don't think there's any danger of assigning it to homework. So exercise 3.2. So exercise 3.2 is sort of a variant on this. It says, if you are given an image, what you do is, I'm going to form this matrix. Let me use the same notation that there is in exercise 3.2. It says that if you are given n data points, capital N data points, then you form a similarity matrix associated with the data. Let's call the points xi, I equals 1 to n. And the similarity matrix Sij, so capital S, this is little Sij, measures the similarity, belongs to the interval 0 to 1, measures the similarity of xi to xj. So if xi is really similar to xj, if they're really similar, Sij equals 1. If xi is very much like xj and is equal to 0 if dissimilar. And you have grace and you have numbers in between. And then you ask yourself, if somebody gives you the similarity, people build these similarity matrices all the time. It's so there are n classes of things here. In recognition schemes, you have apples, oranges, cats, dogs, whatever these classes are. And then here are some images that you're given, and you write down the similarity matrix here. And one might ask oneself, in these similarity matrices, You know, how many, can you cluster, how many clusters are there in these similarity matrices? So ask yourself now, so just stretch your imagination, and actually if you guess, you will guess correctly. And so similarity is really a question of clustering. So let's take some extreme cases where Sij is either 1 or 0, which means they're either really similar or dissimilar. And let us say the first set here are really similar. So it's 1, 1, 1, 1, 1, 1, 1, 1. And the next three are, the next two are really dissimilar. There's 5 entries. And then what do you say? 0, 0, 0, 0. So I guess I should have really. And these two entries were similar, right? I've conveniently separated the first 3 to be really similar and the next 2 to be really dissimilar. I now asked you, what can you tell me about this matrix? What can you say about the rank of this matrix? Huh? Full rank. No. 2, good. Better. Right? So the first 3 columns are all the same, so that's rank 1. And so the number of non-zero eigenvalues is 2. And what is the number of non-zero eigenvalues? What are the non-zero eigenvalues? 3 and 2. Right? And you can figure out what the eigenvectors are and so on and so forth. Okay, so if the entries were all jumbled up here, what could you tell from the rank of S? Number of clusters is the rank of S. And then how do you figure out the clusters if they're all jumbled up? You'll just take the eigenvectors, and all the non-zero entries would give you the cluster. The eigenvectors of the non-zero eigenvalues. The zero eigenvalues are not as interesting. So the eigenvectors associated with non-zero eigenvalues will give you the locations of the clusters. And this is called spectral clustering. There's there's a huge amount of literature on this rather simple story. And you can actually, so okay, this is a completely noise-free case, and Sij equals 0 or 1. So you can soup it up, by the way, if it's between 0 and 1, convert all this to singular values and segment these singular eigenvalues corresponding to the non-zero ones. By the way, the size of the eigenvalues also tells you the size of the cluster. Huh? So here the eigenvalue 3 corresponds to cluster 1 and eigenvalue 2. And it has to do with the fact that there's 3 points together here and 2 points together there and so on and so forth. So that is, I think that I will spare you some of the drama that went in, but this particular spectral clustering excited René Vidal when he was thinking up the, yeah.
Is there a nice canonical example of when it says you're given the S matrix?
Yeah, so in vision, the way they quite often will do this is this capital N here will be these pixels, actually the n squared pixels. And you'll talk about whether a pixel is, how similar it is to the pixel next to it, or even pixels which are a little bit further away. And they'll be based on whether they have the same texture, the same shading, the same color, and you can build all those things into you can have really fancy formulas for this Sij based on your measure of similarity between those pixels. And then, so the way of getting at these eigenvalues and singular values is a way of segmenting the image. Because once you've figured this out, then you have all the segmentation of the image. And there is there's a version of this image segmentation which was pioneered by Jitendra Malik here and Junbo Shi, who is at University of Pennsylvania, called normalized cuts. It's a more graph theoretic way of doing it, whereas this is a matrix way of doing it related to eigenvalues. And there's a lot of literature on eigenvalues of these similarity matrices and so on. This is good enough for you to know, I think. I think the book actually references, in the notes at the back, it actually references it does. I hope it does. If not, we gotta fix it. So the paper is very. Yep. So that's called spectral clustering, and the reason it's called spectral is because you get it out of the eigenvalues, from the clusters of the spectrum. Okay, so I'm going to now do. At least start working on the hyperspaces. So let us say that you were given a subspace arrangement S1 union S2 union Sn, and you knew in addition, you don't know how many things there are, but let us say the dimension of each one of them is one less. So that's the case where they're called hyper. By the way, these subspaces of codimension 1 are called hyperplanes because it's one less than the dimension of the space. So how would you put that in? So a hyperplane is represented by a single polynomial and the single normal. I just want to use the same notation that there is in the book. And so it says each one of the SI's is represented. So Sj, or Si, is equal to the set of all x's in R sub d, where Bj transpose x equals 0, where Bj belongs to R sub d, is the normal. Is the normal vector to Bi. Let me just call that Sj. Normal vector to Sj. And Bj itself, so in fact this looks like Bj1 x1 Bj2 plus Bj2 x2 plus Bj d xd equals 0. So that's what this is. Okay, so what about S1 union S2 union Sn? It's the set of all x's where the product of these, B1 transpose x times B2 transpose x times Bn transpose x, the product of these is equal to 0. Right? It's the same story as before, except instead of x minus mu1, and it's all multivariate. Okay, so this is an unholy mess because you got x1 powers of, but each one of them is linear in x, so the product of them is a polynomial. And the polynomial is, the order of the polynomial is an nth order polynomial. And it is a nth order polynomial where every term has the, so in the entries in it are, it'll have x1 to some power, x2 to some power, xn. There'll be some powers here, some powers here, some powers here, xd to some power. But one thing you can absolutely guarantee is when you add up these powers, let's call them some L1, L2, LD. When you add up L1 plus L2 plus LD, it has to be n, where n is the order of the polynomial there. And the reason that is the case is because every term, there's no unaccompanied terms. Each one of those terms is linear in the xi's, linear in the xi's. So when it comes time to multiply them, if you had 2 x1 squareds, then you'd have one of the fewer powers would be there. And so these are called homogeneous polynomials. That's what it means to be homogeneous. If there was x1, x2, that means if there were 3 variables, x1, x2, x3, and if n was equal to 2, then that means that you'll have terms like x1 squared, x2 squared, x3 squared. You'll have x1, x2, x1, x3, and x2, x3. These are all the homogeneous polynomials of order 2 in 3 variables. And the reason it's homogeneous is 1 plus 1 equals 2, 1 plus 1 equals 2, etc. And when there's the x, so there's no way of getting x1, x2, x3 together because it'll be cubic. Of course, when it's cubic, then so on and so forth. So this story about homogeneous, so if you were to rewrite Pnx, then Pnx is can be written as a so-called homogeneous polynomial. And I'll write, instead of L1, I'll write C, N1, N2, Nd. I should really have used N1 here. X1 to the power N1, X2 to the power N2, Xd to the power Nd equals 0. And this should be over all ni's, with the proviso that sigma ni should be equal to n. I equals 1 to capital D equals n. Everybody with me on this? So I should have really written n1 out here. These are all homogeneous polynomials. And the question is, how many of these are there? How many homogeneous polynomials are there? So question, how many homogeneous polynomials of order n in D variables? And the answer to that is a combinatorial calculation which says D plus n minus 1, and you have to choose n of them because that's this capital N, and that's the number. There are a lot of them. And if capital D is large, even if n is small, there's a ton of them. But conceptually, that's the number of equations. And then, you know, what happens is that even though it's an unholy mess in terms of the powers, this is data. This is what's unknown. So you could write this as some nu n transpose. And this term we called m sub n. And by the way, the set of all homogeneous polynomials of order n in D variables is called, these are called Veronese polynomials. After a wonderful, you know, like in the Renaissance, there were all these guys. Paolo Veronese he's not, it's a Paolo Veronese, according to me, the more famous Venetian painter. But this Veronese was either son of or somehow related to that Veronese. And that Veronese named these polynomials. I don't exactly know why he was interested in algebraic polynomials, but I presume those. So this can be written as nu n transpose times x equals c, where nu n transpose is the listing of all these polynomials. You know, it could be x1 to the power n, x1 to the power n minus 1, x2, x1 to the power n minus 1, n minus 2, or n minus 1, x3, all this. And, you know, there's a way of being systematic about writing these things. It's called this lexicographic order, where you write all these polynomials, x1's big. So anyhow, this is, it's all sort of fussy stuff. But the dimension of this vector is, this vector belongs to Rmn. This vector, it's a transpose of this vector, belongs to Rmn. And it's times c. And c also belongs to Rmn. So what you do is you evaluate nu n transpose at the first data point. I'll call it a superscript 1 because I've used the subscript 1 to mean the coordinates. That's the first data point. Nu n transpose the second data point, and nu n transpose times the nth data point, and stack them next to each other, and it's the same c. And now the dimension of this matrix is m sub n, and the dimension of this is capital N. So, you know, it's just like with the polynomials. You don't know what m sub n is, but you keep building. So let's call this, just an analogy with the previous one, capital V sub n. Keep computing the rank of, so build V1, V2, Vn. The place at which it drops by 1, that's the space at which you got a null space, and that gives you the number of clusters. So n equals min over j, the value of j at which the rank of Vj becomes equal to m sub j minus 1. It just drops by 1. And the assumption, of course, is that capital N exceeds M sub n. Because otherwise, you want to have it be, you want these matrices to be skinny. Lots of data, few clusters. And even though capital N is, even though M sub n grows with little n, I think it's not as big. So the story is amazingly not what you call V sub 1, V sub 2, etc. is a bit of a mess because you've got to write all these polynomials out. But this can all be computerized, right? So you write these polynomials and keep computing the rank. The first value of j at which it drops rank tells you the number of clusters. Once you have the number of clusters, you have C. Now here life is not so easy because once you've gotten C, getting these B1, B2s, BNs is not as trivial, but it's not hard. That's the next step that we will do. And again, if you didn't believe in ranks, you'd still take the singular values, figure out the space at which the singular value dropped by some critical threshold. That would give you the number of clusters. So that is how you segment hyperplanes. And the reason that this hyperplane case was quite interesting is that in computer vision, when you're trying to segment images based on motion and so on and so forth, the motion segmentation ends up being really a case of hyperplane segmentation. And it turned out after we did this that this guy at Carnegie Mellon, Takeo Kanade, with his former student Costeira, had also done something like this, and that I think is referenced. I was just looking at the notes. This Shi and Malik is not. It's referenced somewhere in the book, maybe a little later. But so that I think is you'll see this variant, the story and its variant so many times. But that's really sort of the heart of the matter for the algebraic version of GPCA. And then this code of various kinds that does this, on which we'll send out pointers to, and so which computes these matrices and checks these ranks and so on and so forth. Of course, I got to warn you, when you start doing these calculations, you better be sure that the data is well conditioned, because if these xi's are of vastly different dimensions, then bad things happen. All right. So amazingly, I'm going to end on time. Is there anybody from Merced?
We can.
Oh, I see. Okay. Thank you, Khosrow.